Hey everyone. So as I just said in a little video for my YouTube page, I'm going to be recording some things that are aimed primarily at students and colleagues working on some reading and working on some things together. But since I am using this public platform, I'll try to do my best to at least give folks a sense of what's going on and get as much out of it as they can, especially as you might imagine, some of these first lectures are going to sort of just expand a bit on some of the themes from my algebraic topology lecture series from a geometric viewpoint last year. Yeah, so let me just say what the goal is, and this is in reviewing some a wonderful tool. So the goal for this project is to get as explicit a description of cohomology of symmetric groups with constant but integer coefficients. So these rings are now well known. P by work of myself and Chad Giusti, Paolo Salvatore, and Lorenzo Guerra. They were known additively through homology going back to basically the 50s and 60s, Nakaoka, Cohen-Latame. Yeah, but we want to work over the integers. And let me also say, well, plus some geometry. And maybe you could also say plus, what would also be nice is to start to get a handle fully on configurations of endpoints in our D mod Sn. Sometimes I call that conf var. Again, with Z coefficients. So the point is that as D goes to infinity, these are the same space because the configuration space becomes contractible. Its first homotopy group is basically D minus 1. So as D goes to infinity, these are equivalent. So, so one tool we have is a very explicit explicit and relatively small, certainly relatively small compared to the bar complex, cochain complex. I mean, let me just show you what we're going to be working towards. By the way, these are going to be a little bit more casual, perhaps, and then some of my, the lecture series I gave last spring or in the fall, which was a class. This is kind of a little bit more between friends, although again, we're sharing. So yeah, I'll talk about this, but there's a piece of software that Chad Giusti wrote, and you can just take any list of numbers, and it's going to give you a linear combination of similar lists. The total of these numbers is going to increase by 1, and I claim that this is telling you about the differential in a chain complex that computes, in this case, the cohomology symmetric groups with a simple modification, which is not implemented in code, but easy enough to understand by hand. You also get the same for configurations in finite dimensions. So, let me explain how that works. Let me share the whiteboard again. So I want to explain that tool, and that tool is based on some lovely geometry that goes back to Fox-Neuwirth. And there's a paper, which I'll show you in a moment, that Chad Giusti and I wrote to expand on it. So what we're going to do is we're considering configurations of endpoints in RD And notice one thing you can notice about these spaces is the points have a dictionary order on if the constituent points in the configuration are x1 through xn. Then, for example, this is dictionary order by coordinates. I can look at its jth coordinate is how I'll do that, I guess, borrowing from physicists or maybe not. So for example, if I have 3 points, or I don't know, 4 points here, and this is x1, x3, x2, x4, then you have by their first coordinate, 1 and 3 are most to the left, and then by the second coordinate, maybe I'll reverse their roles. So 3 becomes the first point. X1 is the second point because it shares its first coordinate. Why is that not coming out as well as I'd like? Then x2, and then x4. So there's a dictionary order on points, and the Fox-Neuwirth cells allow one to decompose the space in ways, and essentially sort of via things which share the same ordering. So you get open cells by just having equalities. So what I'm going to do is, let's just, for a lot of today's discussion, I'm going to fix the standard identity ordering. That we'll do pretty regularly today. And then what we want to do is, let me give an example. Then define in this example, consider the points with, say, the first coordinates of the first 2 points are equal, the second coordinates of the first 2 points are equal, the third coordinates are unequal, and that means, by fixing this identity ordering, that x1 is before x2 in the ordering, as it must be. The first coordinate of the third point is not equal. The second coordinate, but it is, say, let's make the first coordinates of the third and fourth points equal. And then let's say their second coordinates are not equal, again, to be consistent with the dictionary ordering of, agreeing with the ordering of the labels. We have that the second coordinate of x3 has to be less than x4. Well, this series of equalities to me has this kind of picture. If these are, say, d equals 3 to draw this, then what we're saying is x1 and x2 share their x and y coordinates, if you will, their first and second coordinates. Their z coordinates differ. X1 is below x2. And then x3 and x4, they differ in their x coordinate, but they have the same x coordinate. And then x3 has to have a lower y coordinate. So I could, let me draw it like this, x3, x4. You notice that x4 has a actual lower z coordinate, but in this ordering, I care about the coordinates as they come in order. And so because x3 has a smaller y coordinate, it comes before x4 in this ordering. So so you can consider the subspace of configurations which satisfy that. And what you notice is that all I need to do to specify this, again with the implicit choice that I'm having my xi's occur in order. So obviously this isn't going to exhaust the whole configuration space, but obviously there's a second kind of permutation then that would let me go further around the configuration space. But this defines a subspace, and the numbers that we would associate to this are, well, the first 2 points share their first 2 coordinates. The second and third points don't share any coordinates, and the third and fourth points share 1 coordinate. So that's 3 numbers that you can associate to this picture, to these conditions. And yeah, remarkably, this fairly simple-minded dictionary order kind of geometry gives rise to a nice way to approach configuration spaces in Euclidean space. So let's get to formal definitions. This is from the paper with Chad. Well, we're gonna modify it. So what we want is a sequence of integers. Again, what we need to do is also, given the sequence of integers, talk about the difference between the dictionary ordering and the ordering of the actual points we have in front of us. But I'm just going to, again, focus only on those which, well, at the moment, focus only on those which come in the dictionary order. So define this subspace of the configuration space, so I'll call it conj gamma. So this is going to be, of course, x1 through xn, such that, and we've basically got 2 conditions to elaborate, and these are what we've just seen, that the ith point in its jth coordinate, that's going to agree with the I plus first point in its jth coordinate for all j less than or equal to the AI. So these AIs, think AI for ith agreement. Okay, so these are levels of agreement between coordinates. Again, you don't care about deeper agreements. You only care about levels of agreement starting at the first coordinate. If my first coordinates don't already agree, I don't care about the second coordinates. But if my first coordinates agree, then and maybe my second coordinates agree, then I'll care about whether the third coordinates also agree or not. So that's these levels of agreement. And then what you say is, well, for them to be in this standard order, then xi in that ai plus 1 coordinate is less than xi plus 1 in this ai plus 1 coordinate. Okay. So, so they agree to some level, and then the second condition is really, again, setting that permutation, saying that these points come in order. Great. So then what's fairly clear is that this is a, so the claim is that conf gamma is homeomorphic to just a Euclidean space of dimension in D minus the sum of the AIs. So the AI is, each AI is giving a codimension AI condition. And so in total, if I've got configurations of endpoints in RD, of course, that's n times D dimensional. And the codimensions are giving me sum of AI total conditions. Okay. And this is as long as all AIs are less than or are less than D. any AI equals D, then of course you're violating the configuration space definition, in which case this is empty. But it's not one of those cases where the empty set works out. You don't get a Euclidean space at all. You get the empty space. Great. So then what we're going to do is now define something which I'll just call W gamma, which is the closure. In the configuration space. And so again, let's repeat. What we have is that xij equals xi plus 1j. Those jth coordinates agree for j less than or equal to ai. But now we have xi plus 1, it's ai plus first coordinate is less than or equal to the xi plus 1, ai plus 1 coordinate. And notice the thing about this is that these are no longer, it no longer imposes the dictionary order. Let me just give a very simple example. It's a non-trivial subspace still, even when, so let's just do 0. So we're looking at configurations of 2 points. This tells me that there's, that either, so we have x1, 1 less than or equal to x1, sorry, x2, 1. And if you think about it, this is a configuration space where, you know, let me draw some possibilities. 1 can come to the left of 2, that's fine. 1 could also be underneath 2, and that would make sense. They're still in order. But also 1 can be over 2. This violates the order, but not the condition that x11 equals x12. It's just that the comparison after that is not part of the game. In a way, we're going down in a stratum, if you will, by considering this equality, but we haven't been making that same inequality demand of the next coordinate. What you can't have is 2 over to the left of 1. So this is a proper subspace. It's about half of the configurations. Well, it would be half the configurations if I only had the ordered ones, because you either are ordered or unordered. But this is sort of more than half. I'm also, it's akin to, well, I mean, configurations of 2 points is RP, well, ordered points is S infinity or SD. And the question is, do you want to include, say, the top cell and the full equator? That's essentially what we're doing with this definition. Or the top cell with just a half equator, that's what would keep us with the ordering. So we're allowing that full equator, which of course is necessary for the cell structure, and that's going to be necessary for a cell structure here. Right. Let's see. We'll give, maybe I'll do a little bit. Let's look back at this example. So here, what you could have is the 3, 4 points could actually come and be in the same plane. Notice that you're still going to be required to have the 1 and 2 points above each other. but you see that there's quite a lot of possibilities of the geometry of those 4 points if that inequality, namely the equality x2 prime equal less than, if that equality x2 prime less than or equal to x3 prime becomes that inequality x2 prime less than x3 prime becomes partial inequality, not strict inequality, x2 prime less than or equal to x3 prime. That equal really changes things. These are no longer cells, but the claim is that and these are things that I haven't written up, so it would be good to sort of to do this at some point. But W gamma is a manifold with corners. That seems pretty clear, even if you haven't played around with manifold with corners a lot. These inequalities, xi less than or equal to xi a plus 1 less than or equal to xi plus 1 a plus 1. Those inequalities obviously are part of a half space, and then multiple ones you get a corner. And it's a submanifold of conf in RD. And then what we want to do is recompose with the projection from conf in RD to conf in RD mod Sn. If we compose with that projection, then we get a map that's no longer an inclusion. And again, I'll give you an example, and the simplest example in just a second. But this is going to be our reference map. I'll call that R gamma. And so this is the kind of object. So R gamma from W gamma to the unordered configuration space of points in RD. This is a manifold with corners over a manifold without boundary. So this is a valid geometric cochain. Again, the kinds of objects that this is a notion that Lipinski shared in a preprint I just learned about 6 months ago, or plus or minus, from Mike Miller, and that Anibal Medina and Greg Friedman and I are working with, proving theorems about. And so then the next claim, conjecture, and this is because we have a version of this. So the next. Is that these W gamma, R gamma, with their boundary maps, form a chain complex. So boundary, by the way, is just taking boundary, which you can do for a manifold with corners. You get a new manifold with corners. And then, which is, of course, it's going to be a subcomplex of what we call the geometric cochains. I often use gamma, but I'll just call it C geom of this configuration space. But then the claim is that that's a quasi-isomorphism. So this is not finite, it's finite degree-wise. Let me just say that. Which models this configuration space, at least additively. there's issues with if you're going to do multiplication, although now we can even start with this phrasing. There's as further videos will say, there's issues with trying to use these W gammas to compute products, but now that I think the W gammas are in firmer footing, that's maybe another question that we can be looking at along the way. So this subcomplex is then isomorphic, and it pretty much is to the Fox-Neuwirth complex. Defined by Chad Giusti and myself. So yeah, let me sort of draw one more example, and then maybe I'll go to our paper for examples, and then I'll show the software. But this becomes, so, sort of a corollary, sort of, well, cohomology of BSN Z is the cohomology of this, the homology of this chain complex. So in a sense, this gives a purely combinatorial way, okay, can we do combinatorics linear algebra ultimately, but combinatorics linear algebra and to get at the homology of this thing. So what's a good example, again, to remember? If I, well, I said before that, let me make it more complicated already. If I have sort of the first 2 points on a line, and by the way, so the point here is that once I've taken the quotient, it becomes a finite to one map, of course, because this is a finite to one covering. And it's generally going to be monic, because if the geometry of the points is agreeing with the different alphas, then you can read off the inequality and determine what it was the point back up in conf gamma that you came from. But for example, this point here, and so this, let me give you a little example of what's going on. This has this point here, if they have share the first coordinates, has one pre-image in conf 1, 2 points sharing one coordinate. That means one has to be less than 2, but 2 pre-images in the boundary of conf 0. So yeah, if we take conf 0, that means that my point 1 is less than my point 2, and you can see that on the boundary you can approach 2 over 1, but the definition also lets 2 and 1 share the first coordinate with 2 down there. So yeah, so that's sort of the subtlety of how we're defining things above these conf gammas. But we, by doing so, actually, it creates these interesting boundary multiplicities down below. Okay. Another simple example that you can kind of visualize by hand. suppose I just have 2 points which share a coordinate and then a third point. So this would be the Fox-Neuwirth cell 1, 0. And what can happen? Well, first of all, these 2 points can actually share an additional coordinate. So maybe I even want to draw this slightly differently. Let's draw it in R3, in which case these two share their first coordinate, but not necessarily their second coordinate. But so one thing that can happen is they degenerate, so to speak, and you get some copies of 2, 0, but there's 2 ways to do that. And so you have to see whether or not those add or subtract. So there's some signs to figure out here, and that's the main work, intellectual work that Chad and I did once upon a time, is to figure out those signs. But we also have, so you degenerate to this. So these actually are a line, or the third point can come in all sorts of possible ways. I'll just put it in blue. And yeah, so those are possibilities. And what Chad and I did, let me do some sharing of the paper first. What Chad and I did was, so here's an illustration, again, somewhat, it's even easier than, simpler than what we were talking about with 1 and 2. Well, they were sharing one coordinate just in the plane. That third point can come in and comes in anywhere sort of between, or before 1, 2, or in the middle of 1, 2, or after 1, 2. So you see shuffles coming in, and that's a big part of the combinatorial structures here. So this is from our paper. And yeah, the main thing we do is very carefully recast the combinatorics. These series of numbers are nice and concrete, but it's better to have trees. And again, for us, this ordering is always just going to be 1, 2, 3, 4, 5, 6. But then, of course, you're going to be quotienting. So we set this up slightly differently, and we use Alexander duality. And we work out signs, and yeah, and we work out the differential. So there is this differential in full detail, and we give a sketch of the proof just using Alexander duality. So I'm now saying that there's an argument where instead of appealing to the 1-point compactification and applying one Alexander duality, we can just look at the configuration spaces and think about this finite subcomplex of geometric cochains, which will more or less involve Alexander duality. If you then are using not the trees but these gamma symbols, then we have this formula for the differential that again involves some shuffles. Let me now just share with you how, here's some examples just to show this is not the easiest combinatorics, and it's not immediately clear. We've got 4 permutations of 0, 1, 2, and 2 here, with very, very different differentials. As we mentioned, there's code. We share it at the end of our archive paper. You can also just contact me if you ever want to play with this code. Let me do so now. Share, just to show you how it works a little bit. So the examples that I was talking about, we had 1, 0. So those 2 points on the left where I'm looking at on the screen, but now I realize that you can't see that screen, but we get -1 times all 3 points having the same coordinate plus 2 zeros. So that's sort of as we saw here. This is the 2, 0 term. This is the 1, 1 term. So all 3 points share the same coordinate. Yeah, and I guess there weren't multiple things because, well, again, low degrees, there weren't a lot of different ways the third point could come into the first 2. So you can, and I have spent some time looking at this code at work. Again, it's hard to get much of a sense, but here's the main thing we're going to be interested in. First of all, honest cocycles, not just mod p cocycles. So here's a mod 2 cocycle, 1, 1, 1. Its boundary is, twice 1, 1, 2 minus 1, 2, 1 plus 2, 1, 1. So this is a mod 2 cycle, but of course it's not an integral cycle. 1, 0, 1 similarly is not a mod 2 cycle, but 2, 0, 2 is. And here's a little further code that Chad put in there to start to look at things where you get the that in its boundary. You can explicitly, well, if you take the difference of these two, you can see that that 4 times 2, 0, 2 is 0 in cohomology. So of course, maybe 2 times 2, 0, 2 is 0 in cohomology, or maybe 1 times 2, 0, 2 is 0 in cohomology. I'm going to tie back to some other geometry in a bit. I wanted to, right, I guess there are no, yeah, so the conjecture, let me go back to the whiteboard then. Let me just make it at the prime 2, and it won't be fully formulated, but so the 2 to the n torsion is going to coincide with Fox-Neuwirth cocycles. I think maybe this isn't all of them, but a large class is you're going to have some sort of block 0, and then the same block, maybe the block is 1, 1, 1. Oh, and it's sort of repeated. So block of let's just say it's sorry, not repeated, it's an even block. So 2, 0, 2 is an example of this, but not 1, 0, 1. So but you could also be looking at things like 2, 2, 2, and then 0, and then the same even block, and then a 0, and then the same even block. And I go out, if I want 2 to the n torsion, I have to repeat, I guess 2 to the n times. So, or 2 to the n minus 1 repetitions. Let me just conjecture it this direction to be clear. I think there's other ways that sometimes you can get higher torsion, but this is going to be a main example. So if, let me once again switch to the code. I don't know, 4, 0, 4, 0, 4, 0, 1, 2, 3. I guess we could just do 2s, but anyways. Gosh, I guess it's not. So it is a cycle. D of it is 0. We have the code set up to look at things with D in its which might limit its torsion. Well, you see that it's complicated. So this is not going to be an easy combinatorics problem. Let me say 2 things while we're here, though. So that's a tool, and of course, this is just an invitation to read the paper with Chad and get used to these techniques a bit. A couple notes. So, of course, well, not of course, these cochains evaluate by intersection. That's the way these geometric cochains essentially map to something like singular cochains. So for example, this 1, 0, 1 cochain evaluates non-trivially on Q1 star Q1, Q1 star Q1, something I've discussed with folks, and you can see this in the original algebraic topology from a geometric point of view. Q1 star 1, Q1 is parameterized by an RP1 cross RP1, mapping to configurations of 4 points in RD. And 1, 0, 1 says I want to search for how many times my first 2 points in the ordering share the first coordinate, and my second 2 points in the ordering also share that coordinate. And so this happens exactly once, right? Whereas, for example, 1, 0, 1 on, say, Q2 star Q0 is going to be 0 because Q2 star Q0, it looks like 4 points, 2 of which are not moving, 2 of which are in sort of 2 dimensions and typical to one another. So yeah, the first condition can happen, but the last points in the configuration will never sort of share their first coordinate. And then one of my favorites is that really started this subject for my approach to it, was thinking about 1, 1, 1 on Q1, comma 1, Q1 on Q1 looks like this. I've got a pair of RP1s being sort of wreathed around by another RP1. There's this bundle, so I get a configuration of 4 points. So this is represented again by taking a RP, or really it's taking an S1 cross over C2 with RP1 cross RP1. And this maps to configurations of 4 points in RD, again, mod S4. And this 1, 1, 1 tells me my 4 points, because I've got 3 different sort of adjacencies of coordinates. My x1 shares its first coordinate with x2, x2 with x3, and x3 with x4. So they all share their first coordinate, which if this were planar, would be happening exactly once. You see in all these parameters, the S1 parameter has to be quote unquote up and down. And so do each of the 2 RP1 coordinates. So, so these geometric cochains, again, directly give cochains and just a cell structure by general theory, but the nice thing about these geometric cochains is if you want to evaluate them on geometric chains or just regular chains, you just intersect, ultimately count how many times your homology class passes through this cohomology class. The other note is that, and this is definitely just a taste of something else that we may discuss, either the we being a smaller group or the a broader lecture. There are, well, so these cochains are similar to iterated bar chains. So for example, people often think about KZ3 as a mysterious object. I like to say it's the third delooping of Z, which if you use simplicial delooping and sort of actually make it more of a cubical model, then this is just a space where I'm taking points in the cube. That's 3 dimensions, that's the same 3, and labeling them by integers. Okay, and the rules are that if the points go to the edge of the cube, they vanish. If they collide, they add. And if they're labeled with 0, you can also consider that as vanishing. So this is a lovely space, a lovely concrete model for the Eilenberg MacLane space, and the same kind of geometry for the configurations is the geometry here, which arises from the iterated bar construction, it works out the same, except at the very end, in configuration spaces, things are not allowed to, oh, I realize, am I not sharing my screen? There we go. So let me go back. I'm not sure how far back I didn't go, but here's the conjecture about 2 torsion. 2 to the n torsion was blocks with 2 to the n minus 1 repetitions. Here's an illustration of how these tome cochains evaluate by intersection, so that the 1, 0, 1 is really sort of looking for 2 points which share their first coordinate, followed by another 2 points which share their first coordinate, which happens exactly once in this 2-dimensional family of configurations where 2 points sort of dance around each other and the other 2 points dance around each other. But that never happens if the 2 points are going around sort of antipodal on an S3, sorry, an S2 instead of an S1, and the other 2 points aren't moving at all. Because of course the points that aren't moving at all, if they're generic, they aren't sharing their first coordinate. And then my favorite example is here, where this class Q11, which is a cycle in the configuration space, consists of 4 points which are parameterized by a circle and 2 copies of RP1. And I take the product, but then I quotient by the antipodal action on S1 and the diagonal action on RP1 cross RP1. That's kind of a wreath product of RP1s, if you will, over RP1. And that defines a 3-dimensional homology class in configurations of 4 points in RD. And that 3-dimensional homology class pairs on this Fox-Neuwirth cochain and cocycle, in fact, mod 2 1 1 1, because exactly once does the sort of the 4 points line up. I'd have to have the top lobe on one lobe on top, another lobe down below, and then I would have the top lobe lined up and the bottom lobe lined up separately. So great. And then as I was saying, my favorite way to think about KZ3 is also a configuration space like model, but now the points are labeled by elements of the integers. And at the end of the day, now, whereas configuration spaces are distinct points, points now can come together, but they add, but that just gives you a different boundary than for these Fox-Neuwirth boundaries. So that's ultimately the calculations of this were probably still the state of the art. But anyways, the initial calculations by Cartan. And I don't know if, it seems like a very similar question to, okay, let's really understand all the higher torsion and the cohomology symmetric groups. It's a very similar question. Can we understand the torsion and the, say, homology of Eilenberg-MacLane spaces? The next thing I'm going to share about are Hopf-ring structures, and they exist in both settings. So, but not for the same reason. Far from intuitive that that they're related. By the way, in this case, if you are looking at, instead of KZ3 or KZN, you're looking at KZ mod 2n, then because there's only one non-trivial group element, you really have an unordered configuration there. And it's you basically get the same homology and cohomology. So that's, you can really say that the Dyer-Lashoff algebra and Steenrod algebra are regradings of quote unquote the same object. I think I touched on that in the lecture series, and I might say more about that too. Okay, thank you, and we will stop.